extended charge distribution, and a point charge. So let me use the remaining time today to set up the paradigm for dealing with a situation like that. And we are going to talk about that more on Thursday, how we would actually do that. All right, so let me set up this situation, the situation that exactly I was describing. Let's say I have some rod that's charged up, and let me make it easy for myself. Let's say it's uniformly charged, meaning in this segment, there's as much charge as there's charge on this segment. And I want to be able to describe how much force is on this ball from this rod. So I have a uniformly charged rod of, let's say it contains some amount of charge, capital Q. And it's going to be interacting with a point charge here, which has some amount of charge, lowercase q. And let me finish the geometrical description of the setup. Let's say they are separated by distance d, and the length of the rod, I feel like that's going to be important, is length L. So suppose someone asks you for what is the force on this charge. How do you answer that? How do you answer? Can I just say, well, force on that electric charge is equal to K times product of the charges divided by distance squared. Can I say this? And the setup of the question is, if that were the answer, then I wouldn't need the 15 minutes, right? So what's wrong with this expression? The distance. Yeah, you don't exactly know. So, when I say d here, I am saying, all right, so this is the distance that matters. Well, that's true for some portion of the charge, but there's this charge here that's, at d plus L. So then your first guess might be, well, why don't we use the average distance? Do it to the midpoint, say d plus L over 2. And there are some special situations where this works. And the example in physics 4a was when you're dealing with the two spherical masses, then you could use the distance between the centers. And that worked out exactly mathematically. When you take things that are more general, like this shape here, using something like this, that doesn't work anymore. So you have to fall back to the basics. You have to you have to use the approach that physicists use whenever we run into a problem like this. We would like a value of distance to use, but there's no one value of distance I can use. So what have you seen me do when faced with situations like that before? Integrate, but that's skipping a step. Integrate means to add things together. What am I adding together? Yeah, so the very first step I'm going to do is I'm going to break up the problem. I'm going to imagine breaking up this entire piece of rod into tiny little pieces of rod. I'm not actually doing it. I'm just imagining that this is made up of very small, tiny pieces of rod. It's too many to draw, so let me just draw a few here. And what you have to imagine is that each segment of rod here, it's a very, very, very tiny piece. I can maybe characterize it with some infinitesimal length, dx. What I can say about this segment of the rod is I know how far this is away from the charge. This is as far away from the charge as the distance x, which is going to range from d to d plus L. Okay? So there's a reason I want to walk you through these steps. Because when you say integrate, usually the biggest problem you will run into is what are you integrating? And so in a problem like this, the most difficult step is actually setting up the integral. with some exceptions, the integral itself is actually not that hard. So let me go through, walk you through this thought process for setting up of the integral. So what I'm telling myself right now is I don't know how to handle the whole rod, but I do know how to handle a small section of a rod. So let me write down an expression for that. So what I'm saying with the small section is that I don't know how to get the whole electric force, but I'm going to be able to get small contribution to the electric force that's coming from this small section of the rod. So I can say that small contribution to the electric force still follows the Coulomb's law. That's K times the amount of point charge times amount of charge that's in this segment of the rod. So let me call that dq for now. It's a small amount of charge in the small segment. Divided by x squared. So this is what I want to integrate. When I integrate this over the entire rod, when I do that, then I'm going to get the whole force. There's a little bit of a tiny difficulty you have to work through first. Anybody see that tiny difficulty that you have to work through inside of this integral? What's the variable that's changing inside the integral? Q is not really a variable. I mean, this is not, but even the big charge Q, like when you look at the small segment, the amount of charge within that is not really what's changing, right? So so dq, this is a symbolic representation for something that you are going to need to replace. So what's actually changing inside of this integral? Yeah, as you go over the rod, the variable that's changing is x. So what you need to do is you need to express this dq in terms of x. Somebody tell me how to do it in next 10 seconds or so. Or in the interest of time, I have to do it. So you will see this often enough, so let me just do it this time. So what I'm going to do is I'm going to introduce the idea of linear charge density. As in, okay, that's the total amount of charge. This is the length. I'm going to say linear charge density is Q over L. That's however much charge is in a unit length. So with the introduction of this idea of some kind of density, what I can say is that this small amount of charge dq, I can say that small amount of charge is equal to the density times the small length that we are dealing with there. Yeah? Does this expression make sense to everyone? Yeah. So I'm going to substitute this in. And then it looks like this. I'm integrating over the rod, k times q times lambda times dx over x squared. Now this is beginning to look like an integral I know how to do. So I'm going to integrate over the rod, and that means I'm going from x equals d to x equals d plus L. So x goes from d to d plus L. Everyone okay with how this integral was set up? Yeah, let me finish it up. So I'm going to pull out everything that's constant. K, Q, lambda. So I have K, Q, lambda. The only thing that's remaining is dx over x squared. What's the antiderivative of that? What's the antiderivative of 1 over x squared? Nope, you skipped one. Okay, let me rewrite it in a format that might be more easier. X to the power of minus 2. Yeah, minus 1 over x. If you're not sure, take this, take the derivative of it. You should get this back. I'm evaluating it the limit. X is equal to d to equal to d plus L. So let me plug all those in. This time, I usually skip steps here, but let me not skip here because I want to make sure that this minus sign is supposed to be there. Is equal to k q lambda times the upper limit minus 1 over d plus L minus minus or plus the lower limit 1 over d. Is this value positive as I'm kind of expecting it to be? Yeah, it's minus over 1 over bigger number plus 1 over smaller number. So, if you wanted to really convince yourself, you can rewrite this as, let me do this. So d times, on the denominator, d times d plus L, and on the numerator, it'll be minus d plus L, so these cancel, so you get just L, the numerator. So, or all of this is equal to k, q, lambda, let me use this, times L over d times d plus L. And hopefully the units work out. This is the force on charge Q. Yep. Any questions? All right, I'm kind of out of time, but let me ask you this one last question. What if someone turned this question around? Instead of asking for the force on the small charge here, somebody turned this question around and asked you for, well, what is going to be the force? Electric force on the rod. Do you believe that the rod will also feel an electric force? Okay, so how do we find this in the next minus 40 seconds? There's a really, so you could go through this entire set of steps all over again to find it, or there's a really quick shortcut to find this right away. Sign me the law of nature that tells you that this has to be true. Which law? You said reaction. Which law does it come out of? Yeah, Newton's third law. So here, what we can say is that because of Newton's third law, when there's an action force, there is going to be reaction force. So this reaction force is going to be equal in magnitude. So Newton's third law, it's a universal law. It holds for every other law of nature that describes forces. Electric force is consistent with the Newton's third law of nature, motion. So when we find this as the action force, then, well, the reaction force, this is the reaction force. It's going to be equal in magnitude to the action force. So if somebody asks you for this, you don't have to go through the whole series of calculation. You can just, well, I know the action force, so the reaction force must be